The concept of a limit in calculus is very important because pretty much everything we talk about in calculus is all derived and based on the limit. So it's really important to get a good understanding of what a limit is. So we're going to start off with the conceptual understanding, and then we're going to work up to more detailed formal definition. Start talking about the idea of a limit. What I want you to do is look at this first graph here, A, where the function is x squared minus 4 over x minus 2. Very broad explanation of a limit is if I asked you to look on the graph of f of x and I asked you to look to see how the function is behaving approximately at x equals 2. In this area, at x equals 2, here's 1, here's 2, what is happening in that area? That's a very broad statement to make about limits. So now, getting more detailed, if I were to look at this graph, if I were to trace it left to right, as x gets closer and closer to 2, what's the y getting closer and closer to? So as I move along this line, tracing it, I'm getting closer and closer to the y value of 4. Now, for a limit, the idea is what is happening to the value of a function as x approaches some number. You don't actually have to reach that value of the function. It's what am I getting closer to? The way that we would write this down, the notation would be the limit as x approaches 2 of f of x is equal to 4. As I get closer and closer to 2, as I come this way from this side, I'm getting closer and closer to the y value, or the value of the function, 4. In general, I would write down as x approaches some value a of a function, what is that getting closer to? L would be the limit, and a is the value of x that you're getting closer and closer to. So looking at this next graph, if I trace it coming from the left, I'm approaching a y value of negative 1. So this notation would look like this. The limit as x approaches 2, but I'm coming from the left-hand side, so where we normally would put an exponent, I'm going to put a little negative sign to state that I'm coming from the left-hand direction of the function g of x. That is negative 1. As I approach the x value 2 coming from the right, now I'm coming from this way, as I trace it, it's going to be 1. So these are called one-sided limits, where I'm looking at just coming from one side. This, where I don't have a direction indicated, that would be a two-sided limit. So you'd have to be coming in from both sides. Now, looking at this third graph, I would say the limit as x approaches 2 from the left of h of x. If I trace this, coming in from the left, there's a vertical asymptote here. So my y value is increasing without bound. I would say that the limit is infinity because it's increasing without bound. Now, if I say as the limit as x approaches 2 from the right of h of x, if I trace it coming from the right, again, this is increasing without bound. The value of the function isn't approaching a specific value. This is the intuitive definition of a limit. You're looking to see, as x approaches some value, what is the value of the function approaching? And that value of the function does not have to exist because the limit is what are we getting closer to? There's many, many ways to evaluate a limit. One way which we're going to start off with, is using a table of values. All right, so in this question, we're going to evaluate the limit as x approaches 0 of the function sine x over x. Since we want to get values that are getting closer and closer to 0, I'm going to start off with negative 0.1. Then I want to get closer to 0, so then I'm going to evaluate it at negative 0.01. And then I want to get closer, so I'm going to keep picking values that keep getting closer and closer to 0. Now, because I'm looking at the negative values that are getting closer and closer to 0, this would be coming from the left side. Then, coming from the right side, I want to pick values that are bigger than 0 coming from the right, but I want to get closer and closer to 0. So I'm going to pick the same numbers. I'm just going to do it on the positive side because I want to be coming in from the right. So now I can use my table function on the calculator, or I can just plug in by hand. I want to find my corresponding function values for each of the x values. When I plug in negative 0.1 into this function, I'm going to get 0.998334. Then I'm going to get 0.999983. Then I'm going to get 0.99999983. Then I'm going to get 0.999999. A lot of nines. So on this side, coming from the left side, it looks like it's getting closer and closer to 1 as x gets closer and closer to 0. Now when we do this for the right-hand side, if I start plugging in values, I'm going to get 0.998334. Then I'm going to get, when I plug in 0.01, I'm going to get 0.999983. And then it's going to keep going. So coming from the right-hand side, the value of my function is getting closer and closer to 1 as x is getting closer and closer to 0. So I can state that the limit as x approaches 0 of our function f of x is approaching 1. Now we can verify this by looking at the graph. If I trace the graph coming from the left, my y values are getting closer and closer to 1, even though the value of the function doesn't exist at 0 because it's undefined. It's getting closer and closer to 1, even though it doesn't exist. And coming from the right, it's getting closer and closer to 1 as well as x approaches 0. To estimate the limit of a function at a given point, looking at a graph, you're literally just going to imagine that you're tracing the graph with your pencil from both sides and imagine what you're getting closer and closer to for the value of your function. So for this first graph, let's find the limit as x approaches -1. So if I'm coming from the left-hand side, I'm getting closer and closer to -1 for my x values, but for the value of my function, I'm getting closer and closer to the value of the function 3. This way, coming from the right-hand side, I'm getting closer and closer to 3. So I'm going to write down and estimate that the limit as x approaches -1 of g of x is equal to 3. Now the actual value of the function, if we look at this, g of x is actually equal to 4, because this is the value of the function. This point right here is open, meaning it's all the points leading up to that, but that point at 3, that point 1 at x equals 1 and y equals 3 doesn't exist. At that point, at x equals 1, the value of the function hops up to 4. So you can see that the value of the limit and the value of the function don't necessarily always have to be the same. The limit is what am I getting closer to? Okay, same thing for the second graph. If I want to find the limit as x approaches 2 of h of x, I'm going to look to see, when I trace it, coming from the left, I'm getting closer and closer and closer to -1. Coming from the right, I'm getting closer and closer and closer to -1. So I'm going to estimate that the limit as x approaches 2 of h of x is -1. Now the value of the function at 2 does not exist. There's a hole there, which means there is no point there at 2, -1. And there is no other value anywhere along x equals 2 for the value of the function. So you can see that the value of the function doesn't have to exist for you to have a limit. Again, for the limit is a constant. There are times that a limit fails to exist. And if you recall, we have one-sided limits, where you're evaluating a limit but coming from one direction only. So for example, if you're coming from the right, a one-sided limit would look like this. So if I was coming from the right and I was approaching A, I would have a little plus sign next to the A to indicate that I was coming from the right, and then my limit, we'll call it L1. If I'm coming from the left, approaching A, then I would have a little negative sign indicating that I'm coming from the left. And I'll call that limit 2. Now a two-sided limit is when you're finding the limit coming from both directions, from the right and from the left. And when we're looking at a two-sided limit, we don't label it as coming from the right or the left. We just label it as x approaches A so that we know it's coming from both directions. Now this limit, the two-sided limit, will not exist unless both the right and the left-sided limits are equivalent. So this only exists if the right-sided limit is equal to the left-sided limit. So now, looking at this example, the limit as x approaches 0 of the sine of 1 over x, if we're doing this by looking at a graph, it's really, really hard to see what's going on as you're getting closer and closer to 0. So, if you look at a table of values for sine of 1 over x, you'll notice that as x gets closer and closer to 0 from the left, these values here aren't approaching any particular number. It's bouncing back and forth all over the place. It's not getting closer and closer to one specific number. And the same thing happens here. If we're looking at it from the right, these values here are not approaching any single number. It's bouncing all over the place. Because the left-hand limit, there is none, and the right-hand limit, there is none. And then in addition to that, they're not equal to each other. We would say that the limit as x approaches 0 of sine of 1 over x, we would say that does not exist. Now we're going to look at finding one-sided limits and two-sided limits by using a piecewise function. If I want to find the limit as x approaches 2 from the left of the given piecewise function, that means I'm looking at values to the left of 2. So I want to make a chart of values using x values that are to the left of 2. So I'm going to start with 1.9, and I want to get closer and closer to 2 and see what the value of the function is getting closer and closer to. So I'm going to pick 1.9, then 1.99, then 1.999, 1.9999. Okay, so when I plug those values in, and because we are doing this to the left of 2, we're finding values that are less than 2. So I'm looking at this first piece of the graph here. So I'm using the rule x plus 1. So when I plug in 1.9, I'm going to get 2.9. When I plug in 1.99, I'm going to get 2.99. When I plug in 1.999, I'm going to get 2.999, and then for the corresponding function value for 1.9999, I'm going to get 2.9999. So as x is approaching 2 from the left, the value of the function is getting closer and closer to 3. So I would say that the one-sided limit coming from the left of 2 would be 3. Okay, now let's look at the right-hand limit. So if I want to find the limit as x approaches 2 from the right of our function, I'm going to be picking values that are greater than 2 but close to 2. So I'm going to be picking 2.1, 2.01, 2.001, 2.0001. I want to keep picking points that are getting closer and closer to 2, but on the right-hand side. When I plug in 2.1, I'm going to plug it in to the second piece because these are the x values that are greater than 2. So I'm going to plug in 2.1, and I'm going to get out 0.41. Then I'm going to plug in 2.01, and I'm going to get 0.0401. When I plug in 2.001, I'm going to get 0.004001. Whoops. And then when I plug in 2.0001, this is what I'm going to get. So, as x approaches 2 from the right, the value of my function is getting closer and closer to 0. So I would say the limit as x approaches 2 from the right for this piecewise function is 0. Now we can verify that by looking at the graph. Let me use my green. If I'm coming from the left, I'm looking at my green table. And if I'm coming from the left, as x gets closer and closer to 2, I'm getting closer and closer to my y value of 3. And then coming from the right, as I get closer and closer to 2 for my x, I'm getting closer and closer to 0 for my y value. Now, the two-sided limit would be if I'm looking at both sides coming in at the same time from either direction. I would say as x approaches 2, but I'm not specifying a specific direction. I would say in this case, the limit doesn't exist because in order for the two-sided limit to exist, the one-sided limits have to be the same. You have to be approaching the same number from either direction. So you could have one-sided limits that exist, But the two-sided limit, when it's coming in from both directions at the same time, in order for that to... Okay, now we're going to talk about limits that approach infinity or negative infinity and how they're related to vertical asymptotes. So a vertical asymptote at x equals some value, we'll call it a, occurs when one of the two situations happen. You could either have the one-sided limits as x approaches a from the left of a function, if that approaches positive or negative infinity, and if you have the same thing coming from the right, if it approaches positive or negative infinity, then you would have a vertical asymptote at whatever that value is at x equals a. Now, because it's a vertical asymptote, remember, vertical lines have equations, x equals, and then whatever the value of x is, that it passes through all those x values. The other case that you could have is if you have a two-sided limit as x approaches a. If that's positive or negative infinity, then you would have a vertical asymptote. So if we look at this graph, I have a vertical asymptote here at x equals 0. I'm going to abbreviate VA for vertical asymptote at x equals 0. And I know that because I have the first situation where I have the limit as x approaches 0 from the left of f of x. That limit, let me trace it here in purple, as I come from the left and I come down, I'm approaching minus infinity. And then coming from the right on the graph, let me trace that in purple. Coming from the right, approaching 0, I'm going up without bound, so that would be positive infinity. So your vertical asymptotes occur when you have limits, either one-sided or two-sided. In this last video, we're going to step back and look at the big picture and look at all the key topics that we talked about in this section. And so in the first video, we talked about what a limit was. And really what we're doing when we're evaluating a limit is we're trying to determine the behavior of the graph at that value of x. So if we look at the graph and we answer these questions, comparing it to the graph, the first question is asking about the behavior of the graph at x is equal to -4. So we have the one-sided limit, then the two-sided limit, and then the value of the function. So as I look at the graph and I approach -4 from the left, it looks like we're approaching a function value of 0. When I approach -4 from the right, we're approaching a value of the function as 0. Now, because the one-sided limits are the same, that means the two-sided limit is going to exist, because coming from both directions, the two-sided limit will be 0. Now, if I look for the value of the function at -4, when x is -4, I can clearly see from the graph that the value of y is 0. Okay, in the next example, we're looking at the behavior of the graph around -2. So as I approach -2, I'm doing this one in purple, coming from the left, it looks like I'm approaching a y value of 3. Coming from the right, it also looks like I'm approaching a y value of 3. And because the two one-sided limits are the same, that means the two-sided limit will also be 3, because coming from both directions, from both sides, the limit is 3. Now, the value of the function at x equals -2 does not exist. There is an open circle at on the graph at x is equal to -2, which indicates to me that there's a hole in the graph and a missing value there. So there is no -2 in our domain for this function. Looking at the next line, we want to look at the behavior of the graph around 1. If I approach 1 from the left, it looks like I'm approaching y value of 6. Approaching 1 from the right, it looks like I'm approaching a y value of 3. Now, because the one-sided limits are different, the two-sided limit is not going to exist because it's coming from two different sides. There's going to be two different values. Okay, now the value of the function at 1, if I look at x is equal to 1, there's an open hole at y is equal to 3. So the value doesn't exist at the point 1, 3, but it does exist at the point 1, 6. So my value at x equals 1 for the function would be 6. All right, last example. We're looking at the behavior of the graph at x equals 3. And if you notice, even though it's not written in there, we can visualize that there is a vertical asymptote at x equals 3. If I approach the graph, if I approach x equals 3 from the left, I'm decreasing without bound. So my one-sided limit as x approaches 3 from the left is going to be -infinity. Coming from the right as I approach x equals 3, I'm also decreasing without bound. So that's also going to be -infinity. Because the two one-sided limits are the same, I can say that the two-sided limit is also -infinity. Doesn't matter which direction you're coming in from, your limit as you approach x is 3 is going down. You're going to -infinity. Now, because there's an asymptote there at x is equal to 3, there's no value of the function, so we would say that this does not exist. There's no value of the function